You are on a commercial rooftop. The manifold gauges are hooked up, and they are reading abnormally low suction and low head pressure. Down the line, ice is rapidly crystallizing across the copper pipe. You have an immediate diagnostic dilemma. Is the system leaking refrigerant, or is a severe airflow restriction suffocating the evaporator coil? Guessing wrong here results in wasted refrigerant, permanently frozen coils, or a compressor destroyed by liquid slugging. This gauge shows a pressure of 134 psi, but that number is a static variable. To determine system health, we must calculate the saturation offset to see how the refrigerant is actually behaving during a phase change. To do that, we have to map the baseline refrigeration loop. We will derive two critical metrics, superheat and subcooling, using saturation temperatures, and then apply those numbers to a diagnostic matrix. Understanding these invisible thermodynamic states allows a technician to move beyond guesswork and evaluate the system based on its actual mechanical performance. This diagram illustrates the closed refrigeration circuit. Its primary objective is transferring heat from the indoor environment to the outside, using a refrigerant as the working fluid. The cycle begins when low-pressure vapor is pulled from the indoor evaporator coil into the outdoor compressor. The compressor's mechanical action squeezes this gas, discharging it as a high-pressure, high-temperature vapor. This hot vapor travels into the condenser coil, where it releases its heat to the outside air. Losing that heat causes the refrigerant to undergo a phase change, condensing into a high-pressure liquid. The high-pressure liquid then travels down the line and hits the expansion valve, also known as the metering device. This valve forces an abrupt drop in both pressure and temperature. The refrigerant is now a cold, low-pressure mix, prepared to absorb heat. Finally, the cold liquid enters the evaporator coil inside the indoor unit, absorbing ambient heat from the room air until it boils back into a vapor, and the cycle repeats. This entire continuous cycle relies on successful phase changes. If the refrigerant does not fully vaporize, the compressor will be destroyed by liquid. If it does not fully condense, the expansion valve cannot accurately meter vapor. To understand those phase changes, we have to define saturation. Saturation is the condition inside the evaporator and condenser coils where liquid and vapor exist simultaneously. This diagram compares evaporation to boiling. Liquids at saturation are full of kinetic energy. They have reached their boiling point, where their internal vapor pressure equals the surrounding atmospheric pressure. This creates the pressure-temperature, or PT, relationship. In a closed system at saturation, knowing the exact pressure of the fluid allows us to determine its exact boiling or condensing temperature. You can see this on a PT chart or directly on your gauge ring. If you have a physical pressure reading of 132 psi on an R22 system, the saturation temperature is 75 degrees Fahrenheit. Establishing this saturation baseline is mandatory. Without knowing the exact temperature where the refrigerant changes state, calculating how efficiently the coils are working is impossible. Once we have our baseline, we can measure deviation. The first metric is superheat. This is the amount of heat absorbed by the refrigerant after it has completely boiled into a vapor on the low-pressure side. The physical temperature rises above the saturation point. To find this value, take the physical temperature of the suction line and subtract the saturation temperature derived from your pressure gauge. A healthy system usually targets a superheat between 8 and 15 degrees. This margin ensures that 100% vapor enters the compressor. On the high side, we measure subcooling. This is the amount of heat rejected from the refrigerant after it has completely condensed into a liquid. The physical temperature drops below the saturation point. To calculate this, take the saturation temperature from your high-side pressure gauge and subtract the physical temperature of the liquid line. The target subcooling is typically 10 to 15 degrees. This ensures a solid column of pure liquid reaches the expansion valve. Calculating these two temperature deviations allows us to quantify coil efficiency and verify the system is operating within safe mechanical limits. Field diagnostics require a specific order of operations. Never trust your refrigerant readings until the system's airflow is verified. The evaporator coil needs between 350 and 450 cubic feet per minute of air flowing across it for every ton of cooling capacity to function correctly. This diagram shows the measurement of static pressure. You must verify the filter pressure differential to identify blockages before adjusting the refrigerant charge. Once airflow is confirmed, the system must run under load for at least 15 minutes. This allows the phase changes inside the coils to stabilize. Running a diagnostic matrix on a system with failed airflow will result in incorrect conclusions regarding the refrigerant level. Let's return to the scenario where the manifold gauges show both low suction pressure and low head pressure. This reading could be caused by a lot of refrigerant or simply a lack of room heat. This matrix maps out the fault patterns. With a low charge, the underfed evaporator boils off the limited refrigerant too early, resulting in high superheat. Because the condenser is underfilled, the subcooling will be low. With a low heat load, the physics change. Because there isn't enough heat entering the evaporator to boil the refrigerant, the superheat will be low or non-existent. Subcooling, however, remains normal because the full charge is still present in the system. By calculating the subcooling, we can differentiate between a leak and a low-load environment, preventing the unnecessary overcharging of a healthy system. In a different scenario, your gauge might show low suction pressure while the head pressure appears normal. This pattern, low suction pressure combined with low superheat and normal subcooling, identifies a specific mechanical failure. This is an evaporator airflow restriction, typically caused by a dirty filter, an iced-over coil, or a failed blower motor. Without warm air crossing the coil, the refrigerant cannot absorb heat, resulting in low suction pressure and low superheat. Meanwhile, the outdoor condenser maintains a normal subcooling metric because its heat rejection process is unaffected. Raw pressures report the current state of the refrigerant. By deriving superheat and subcooling against the saturation baseline, we identify the specific mechanical cause of the system failure.